All right, great. Well, it's a pleasure to be here talking to you today. I'd like to thank the organizers for the chance to talk to you guys, and of course, all of you for being here. You're the ones who make the summer school, and so it's great to have such a good community. So thank you, Nima, for that nice introduction. I should say, my first encounter with Nima came when I was a freshman in college, and Nima gave a colloquium on deconstructing dimensions. And that was the first time in my life that my mind was really totally, completely blown. So Nima ruined everything else in the world for me, and I had to do theoretical physics after that. So I want to start with two apologies. One is that I picked up some sort of plague last week in Italy, so my voice is a little weak, but if you can't hear me, just let me know. The other is that I severed the nerves in my arm 10 years ago that lead to the back of my arm, so I can't actually write above my head. So if you have a hard time seeing what I'm writing on the board, again, just let me know. But I'll try to sort of maneuver the boards in a way to make the writing clear. All right. So I've been asked to talk about my favorite subject. That's the one that gets me out of bed in the mornings, which is naturalness and approaches to the hierarchy problem. And what's fun about giving these lectures, and hopefully interesting for you guys, is that the nature of this sort of talk at a summer school, these sorts of lectures at a summer school, were pretty much scale invariant for 30 years, right? So for 30 years, you could more or less give the same set of talks, and the talks would be about the hierarchy problem, and then they would be about supersymmetry, and you'd spend most of your time talking about supersymmetry, and then maybe if you were Italian, you would talk about global symmetries and composite Higgs models, and you would be done. But over the last few years, we're in this really interesting situation where we've had all of these familiar models over the last 30 years. They have a lot of very robust predictions. And we're now comparing them to data, right? And data is saying that either the ideas are not there in the incarnations that we had in mind, or that they don't work as well as we had initially imagined them to. And from a theorist's perspective, when data does that to you, right, you can stick to your idea and try to think if there's ways to tweak it. But the better thing to do is to ask whether there are other ideas that you haven't contemplated yet. And so we're in this magical period. It's funny to say that null results are magical, right? But we're in this magical period where, because null results are unseating the historically dominant ideas, now is the time to be writing down new ideas. And I'm getting old and slow, and so what's great is that for you as young people, now is your chance to absorb lots of different ideas and to come up with your own approaches to the hierarchy problem. So what I want to talk about today, or what I'll talk about over my 3 lectures, loosely speaking, I don't know exactly how it's going to get blocked out in terms of the timing. But first thing I want to do is just talk about what is the hierarchy problem. Oh man, this is going to be hard with my arm. OK. All right, so what is the hierarchy problem? Most of us know, of course, what the electroweak hierarchy problem is. But it's worth thinking very clearly about what the actual problem is. So there are a lot of famous people in our community who are actually a little bit confused about what it means. And that's because for a long time we haven't had to think too carefully about it. But now we have to think carefully about it. And so I want to at least spend a little bit of time on framing the problem in an appropriate way. The next thing I want to do, once we have a hierarchy problem, is talk about old solutions. OK, so we've had the hierarchy problem for as long as we've had the standard model, if not longer. And that means we've had a lot of time to work on solutions. So the canonical solutions, of course, are supersymmetry, global symmetries, lowering the cutoff of your standard model effective field theory, and using anthropic reasoning to explain the value of the weak scale. So I'll talk about those old solutions. This will be most of today's lecture, and a little bit of this today. This will be some of the second lecture. And then I want to talk about new solutions. So these are things where the detailed models have really, or the ideas have only really been articulated over the last few years in response to null results and data. So these will be ideas like neutral naturalness, and also ideas like the relaxion. I will take a somewhat critical approach to the relaxion. So the relaxion is really one of the most fantastic new ideas we've had in the last few years. But as with any truly new idea, it has lots of problems, and it's worth being honest about them. And maybe one of you will figure out a framework that works very well. And then I want to end with rampant speculation. Which mostly amounts to telling you about some ideas that sound really good, but no one's figured out ways to make them stick in the right way for the electroweak hierarchy problem. And that's the invitation for you guys to actually make these come into play. So some of these ideas will include things, also in new solutions, I'll talk a little bit about naturalness, so Nima can yell at me for misrepresenting his ideas. And under rampant speculation, I'll talk a little bit about using disorder to solve the hierarchy problem. I will try to talk a little bit about UV-IR mixing to solve the hierarchy problem. And if I have time, I'll try to talk about self-organized criticality. OK, so it should be fun. Feel free to ask lots of questions. Again, if you're familiar with the hierarchy problem, hopefully today you find a little bit like a glass of warm milk. And at least that'll get us all onto the same page. All right. So to understand what the hierarchy problem is, we first have to start with a notion of naturalness. The hierarchy problem is somewhat unique. Well, it's one of a trifecta of problems in the standard model that don't come from incontrovertible evidence like dark matter or neutrino masses. Those are places where we know there's something there, and it forces us to extend the standard model. They're not even on the same footing as things like gauge coupling unification or inflation or baryogenesis. Those are problems where we have very suggestive hints that there's some mechanism at play, given data that we actually see in the universe. But rather, they're in the class of problems that just amount to a conflict between our theoretical expectations for the size of parameters and the actual sizes of parameters that we see in nature. So those three problems, of course, are the strong CP problem, which Michael is and will continue to be telling you about, the cosmological constant problem, which I don't know if anyone's telling you about in this program, and the hierarchy problem. OK, so these, again, are all problems where it's a conflict between our expectations for the size of parameters in quantum field theory and what we see. And those expectations really have a sort of two layers, all right? So the first layer of naturalness expectations actually is due to the Dirac. So Dirac had this idea, which turns out to be very well justified in the context of quantum field theory, that if we have, in a theory with a fundamental scale lambda, that is to say, we imagine, as we always imagine with quantum field theory, that the theory is defined in the far ultraviolet at very short distances. And then all we're interested in doing after defining the theory is seeing what it does as we take it to longer and longer distances. All right, so we imagine defining the theory at some scale lambda. If it has some operator that appears in the theory, so there's some Lagrangian that has some coefficient in front of that operator, right? Then the size of the coefficient, the natural size of the coefficient, Dirac claimed, should be an order 1 number in natural units times whatever the fundamental scale is, assuming we're working in 4 dimensions, to 4 minus the scaling dimension of the operator, right? That's just dimensional analysis, right? We just say the operator has some scaling dimension, so this coefficient has whatever mass dimension it takes to get us up to the mass dimension of a Lagrangian density. So we're saturating all of our dimensionful scales with the fundamental scale, and then all dimensionless parameters are going to be order 1. And again, this is something we learn in kindergarten to do dimensional analysis. That's all of our scales in the problem, so it should saturate the size of the coefficient. But in quantum field theory, of course, it's deeper than that, right? In quantum field theory, the actual notion of radiative corrections and normalization tells us that all quantities are connected. And so unless there's something very special about the theory, once you compute the radiative corrections to a theory defined at a fundamental scale, those radiative corrections will organize themselves into this form. OK, so this is Dirac naturalness. It's our original notion of naturalness. And it's the one around most of which our naturalness expectations are constructed. Now, of course, if that were it, we would kind of be in trouble, right? Because we see in quantum field theories in nature, we see lots of different parameters that don't satisfy this criterion of Dirac naturalness. All right, so 't Hooft came along and articulated a more refined version of this naturalness. All right, so there's a notion due to 't Hooft, what we often call technical naturalness. And technical naturalness absorbs the notion that, of course, in addition to scales and interactions in a quantum field theory, there are also symmetries. And as long as we have a symmetry of the quantum action, that is to say, we have a symmetry that is not just a symmetry of the classical Lagrangian, but is in fact also a symmetry of the quantum theory. All right. Then if there's a symmetry in the quantum theory, then that controls the form of counterterms. It controls the form of radiative corrections. And the same sort of quantum democracy that gave us Dirac naturalness will actually respect any constraints or selection rules imposed by the symmetry. So the particular notion is, if you have an operator, or if you have an operator coefficient, where if you take that coefficient to 0, the theory has some new enhanced symmetry, then the natural size of the operator coefficient, you can write it as some parameter, which I'll call S, times an order 1 number, again, times this just dimensionful power counting. Where now this, you can think of this parameter S as something as a spurion that parameterizes the violation of the symmetry by the non-zero value of this parameter, okay? And if this spurion, of course, is much less than, say, the fundamental scale, well, in this case, I've written it in a dimensionless way, but if it can be a small dimensionless number, and that corresponds to a small controlled breaking of whatever symmetry is manifest when the coefficient is taken exactly to 0. Okay. So the reason this appears in your expectation for the natural size of operator coefficients is that, again, if the operator coefficient were 0, if S were 0, then there would be an enhanced symmetry. Radiative corrections would respect it. If the symmetry is broken by a small amount, proportional to a non-zero value of S, any radiative corrections have to be proportional to that breaking. And therefore, even after renormalization, the renormalized values of the parameters will be proportional to the breaking. All right. So this allows you to understand if you have a parameter that would give you an enhanced symmetry when it were 0, if you can then generate a small breaking of that symmetry, you can understand the existence of small quantities. Now, there's something of a difference between these two levels of naturalness. They're weaker conditions, right? Dirac naturalness just tells you, you write down a field theory, you get some expectations for the size of coefficients. H'toof naturalness tells you, well, if there's a symmetry that's manifest when a coefficient is taken to 0, that coefficient can be small. But if it is small in nature, if you go out in nature and you observe one of these coefficients and you find that it's much smaller than its natural value, you don't worry about it in the context of quantum field theory, but you would still like to explain it. Okay, you would still like to know why it's smaller than the Dirac natural value. And we'll consider 2 examples where this sort of logic is completely manifest. Okay. There are lots of subtleties, by the way. I've been somewhat vague about what I mean by symmetries that are manifest when a coefficient is taken to 0. There are lots of subtleties about what counts and what doesn't count. And throughout the rest of my lectures, we'll really try to be specific when it matters about what symmetries count for technical naturalness criteria. Okay, it'll come up in particular in a very sharp way when we talk about the relaxion, but it will also come up in various other contexts. Okay. So these ideas appear really everywhere that we see quantum field theory in nature. They appear in beautiful ways, of course, in condensed matter systems, which are really our laboratories for quantum field theory. But they also occur very specifically in the context of the Standard Model, which is high-energy field theorists as particle physicists. That's really all that we have. So what are those 2 manifestations? Let me just give you 2 examples so you can understand how they work. So the first example is an example of Dirac naturalness. It's actually the problem that Dirac started thinking about as soon as he appreciated the notion of Dirac naturalness. And he just wanted to understand, he knew that there was a mass scale associated with gravity, right? So he knew we had the Planck scale up at 10 to the 18, 10 to the 19 GeV. And he also knew that we had protons down around a GeV. And so Dirac wanted to know, why is it that there is an 18 order of magnitude hierarchy between the mass of the proton and the mass of the Planck scale? Now, Dirac's answer to this question was very wrong. But that's not Dirac's fault. It took really the understanding of asymptotic freedom in the strong interactions to really get a good answer to this question. But once we know the answer to the question, it's such a beautiful manifestation, not even of technical naturalness, but of the original notion of naturalness itself. So what's the answer? Well, the answer we know is that if you imagined just taking QCD, you can set aside the rest of the Standard Model for the time being. In the far ultraviolet, let's say defined around the Planck scale, that theory consists of course, just the SU3 strong interactions. And we have 6 flavors of light quarks. What we understand, of course, is that given this non-abelian gauge theory, if we define it at some scale with some coupling, then of course we can study how the coupling evolves as a function of scale. And in particular, the way we've constructed the theory, defining the theory at the Planck scale, The only thing interesting that happens as we go down in energy scales is that we crossed several mass thresholds corresponding to the masses of various fermions. But until you start to hit, for example, the top mass, right, there's just a long desert of energies, and all that happens in that desert of energies is that the coupling of the SU3 interactions runs logarithmically. Okay, so we know how to work out the details, right? We can go ahead and we can compute the beta function. So we can compute it at whatever loop order we're powerful enough to compute at. So this, of course, is the one loop piece. It has a beta function coefficient that just depends on the size of the gauge group and the number of flavors. We could go ahead and compute higher order pieces if we wanted to. But at one loop, at least, it's convenient because we can go ahead and we can solve the beta function directly to actually find the value of the coupling at some scale relative to a scale at which it's defined. Okay, so we can solve the one loop beta function. We can imagine we've defined the theory at the Planck scale. So there's some value of the gauge coupling at the Planck scale. And the difference between that value of the coupling and the value at any other lower scale mu, right, is actually just going to be given in terms of the one loop beta function coefficient times the logarithm of the scale. Okay, so this is something we know and love. We learn it in our first year of quantum field theory, which might be first grade for some of you, and it might be graduate school for others, and that's all good. So the notion is, given the coupling at some scale, I've written in terms of the inverse because that's the natural way of solving the RGE, there will be some logarithmic evolution of the coupling. Of course, with the sign of the beta function, we know what happens. As we go to the far infrared, the coupling grows and grows. And that means at some point, of course, at least at one loop, nominally there's a scale, mu, at which this coupling diverges. Okay. So we can just take the scale at which that happens to be the scale at which 1 over the coupling vanishes. All right, so that defines a scale, which we'll call lambda QCD. Of course, those of you who study QCD know that this is a pretty poor definition of lambda QCD, but it suffices for our purposes. So that's just we take to be the definition of the scale at which 1 over the coupling goes to 0. Okay, so now we can go ahead and solve this for the actual coupling itself, or for the scale itself. We find that the scale lambda QCD is equal to the Planck scale, and now it's leveraged by an exponential factor that depends on the coupling that was defined in the Planck scale times this one loop beta function coefficient. Okay, so this is a beautiful result, right? It tells us we started with a fundamental scale in our theory, the Planck scale, at which we defined our QCD, and we started with some value of the gauge coupling at that scale. And then we find, just from the logarithmic evolution of the coupling, of course, that it spits out an exponentially different scale that we associate with strong coupling and confinement in QCD. All right. Good. So this is an amazing result, right? So this is known as dimensional transmutation. And it answers Dirac's question, right? Okay, in detail, right, what it actually means is if we have light flavors of quarks, then of course the light flavors of quarks after confinement give us things like all of the different baryons, of which the proton is just one of them. The mass of the proton parametrically is of order the confinement scale. And so the reason why, of course, the proton mass is much smaller than the Planck mass scale is that logarithmic evolution of a gauge coupling has given us 2 exponentially different scales. And it's the exponentially smaller one that gets the mass of the proton. Okay, so this is a beautiful triumph of Dirac naturalness, right? At the fundamental scale, all right, we just had a theory where the only thing that was really of interest to us was the dimensionless value of the gauge coupling. That could be order 1 at the Planck scale. Logarithmic growth of that coupling into the infrared gave us a new scale that was exponentially different. And that now allows us to understand the existence of an emergent scale that was not defined in our fundamental theory, but came out purely as a result of dynamics. Okay, so that's a beautiful example of Dirac naturalness. Of course, it's not the only beautiful manifestation of naturalness that we see in nature. We also see nice examples of naturalness, and particularly technical naturalness, in the context of the Standard Model. So another question you might have when you look at the Standard Model is why the masses of fermions have such widely different values, right? You might worry that somehow this, of course, is also a violation of our expectations of naturalness. So in particular, if we look at the Standard Model, right, we see that between the electron and the top quark, there's something like 5 orders of magnitude. If we look at the neutrino masses, saying the largest value of the neutrino masses allowed by current data, that gives us a hierarchy on the order of 10 to the minus 11. this also nominally seems to be a vast violation of our notions of Dirac naturalness. So it's also a good question where these numbers come from. And these numbers turn out to be an example not necessarily of Dirac naturalness in the standard model, but at least a beautiful manifestation of technical naturalness. So what's the idea? Well, we know in the standard model these fermion masses are actually coming from Yukawa couplings, right? So the Yukawa couplings are just dimensionless parameters that couple the Higgs, say, to various species of left-handed vial fermions in the standard model. And of course, when the Higgs gets a vacuum expectation value, that marries up the fermion degrees of freedom to give us massive Dirac fermions. So you can ask yourself the question, OK, if the masses are coming from the Yukawas, so these mass ratios are just ratios of Yukawas. Now you can ask yourself the question, all right, well, if I take the Yukawas to 0, is there an enhanced symmetry of the theory? And if the answer is yes, then of course, we at least are able to understand from the notion of a 't Hooft that there's a stable numerical hierarchy in the values of Yukawa couplings that might be radiatively stable. So we might not understand why there's a numerical hierarchy in the first place, but at the very least we could understand, given a numerical hierarchy in the fundamental theory, we could understand that it's preserved by quantum effects. OK. So of course, famously in the standard model, if I take the Yukawa couplings to 0, there is an enhanced symmetry of the theory. The enhanced symmetry of the theory is a U3 to the 5th symmetry. That corresponds, so the reason why it's a 3 is that we have 3 generations, and then 5 comes from the fact that there are 5 types of left-handed vial fermions in the standard model. There's Q, U, D, L, and E. And so for each of those, we can arrange the 3 generations into something that transforms under the fundamental of the U3. Now, it's convenient actually to express the symmetry not in terms of the U3 to the 5th, but in terms to peel off the U1 factors and arrange them in different linear combinations. The reason why that's convenient is because it matches on to some of the accidental symmetries of the standard model. So this full U3 to the 5th symmetry, it's convenient to write as SU3 symmetries that rotate each of the 3 generations of left-handed vial fermions into each other. So there's an SU3 for each of QU, D, L, and E. And we've stripped off the U1 factors. So the U1 factors are convenient to write as baryon number, which we know is a nice accidental symmetry of the standard model, lepton number, hypercharge, a PQ symmetry, which Michael has or will tell you about, and then a funny extra U1 that corresponds to rotations of the free right-handed leptons. OK, so this is the full set of global symmetries of the standard model in the limit where we take the Yukawa couplings to 0. Some of them, of course, are anomalous, but at least the part we're going to be interested in for talking about Yukawa couplings is this first bit, right? So these first sets of symmetries become manifest in the limit where we take the Yukawa couplings to 0. So we see we're going to have some version of 't Hooft's notion of technical naturalness. We take the Yukawa couplings to 0. There are enhanced symmetries of the theory. Of course, if we turn on the Yukawa couplings, these symmetries will all be broken down. And what's convenient in terms of then to understand how the theory should organize itself under radiative corrections is to do a spurion analysis. So again, the idea of a spurion analysis is if you have a symmetry of the theory that's manifest when a parameter is 0, you then treat the parameter as a field. You promote it to a field. And you could imagine, for example, the parameter itself being an expectation value for that field. And you assign that field whatever global symmetry charges it needs in order for the interaction that breaks the symmetry to actually be invariant to the symmetry. OK. So for example, here we see I've claimed that if we turn the Yukawa couplings off, we get this fully manifest symmetry. We could imagine that when the Yukawa couplings is turned on, the symmetry would be manifest if the Yukawa couplings transformed in the following way. So if the up-type Yukawas transformed like in the fundamental of the SU3Q, and the anti-fundamental of the SU3U, and if there were singlets under SU3D. OK, so I'm going to write this shorthand as transforming. This is the transformation properties of the up-type Yukawas under the first 3 of the symmetries. Those are the symmetries acting on the quarks in a standard model. Similarly, the down-type Yukawa could be a spurion transforming, again, in the fundamental of SU3Q, the anti-fundamental of SU3D, and there's a singlet under SU3U. Okay? So for example, to see how the spurion analysis is working, right, this is the form of the uptype Yukawas. So Q is transforming it as an anti-fundamental, U is transforming as a fundamental. If the uptype Yukawas transform in a specified way, then the entire Yukawa interaction is an invariant under those flavor symmetries. Similarly with the down-type Yukawas, and then finally the lepton Yukawas. If they transform as a fundamental under the SU3 acting on the lepton doublets and an anti-fundamental under the lepton singlets, then the lepton Yukawas, those are the spurious charges of the lepton Yukawas. Okay, so now we imagine, right, the Yukawa couplings, their numerical values correspond to expectation values of these fields with these spurious transformation properties. We can think of that as a spontaneous breaking of these sets of global symmetries. And now that gives us a bunch of selection rules that tells us under quantum corrections, right, all radiative corrections that come from the breaking of these flavor symmetries have to be proportional to the Yukawa couplings, and they have to be the occurrence of those radiative corrections have to be specified by the spurious charges. Okay. So it gives us a set of organizational rules. Now we can go ahead, even without manifestly computing radiative corrections in the theory. We know that because there is a manifest symmetry that is broken by the values of the Yukawa couplings, their particular pattern of breaking gives us selection rules. Radiative corrections respect those selection rules. All right. So that tells us, among other things, when we actually normalize the theory, there will be quantum corrections, but the quantum corrections will be proportional to the values of the Yukawa couplings themselves, and it will preserve a notion of technical naturalness. Now, that doesn't, of course, we're physicists, we're curious about not just whether our quantum field theory respects the values of hierarchies that are in the quantum field theory, but where those actual hierarchies come from. So this notion of technical naturalness, it doesn't tell us why the electron is so much lighter than the top quark. It just tells us that if in the fundamental theory the electron Yukawa is made much smaller than the top quark Yukawa, then we can understand as we flow to the infrared of the theory, that relationship will be preserved. Okay, but there's a whole field, of course, of flavor model building that is not concerned, is happy that this is technically natural, but now wants to make it, in fact, Dirac natural. So wants to write down some underlying theory that gives you all of the numerical values of the Yukawa couplings. Okay. So that's just to say, if you have a theory where a parameter is technically natural, if it's small, you can be satisfied there's nothing wrong with your quantum field theory, but you may still wish to explain why those parameters take on the values that they do. Okay. So hopefully this at least gives you a feeling for these two notions of naturalness, two different ways in which they're manifested in the standard model. Dirac naturalness is beautifully realized in the smallness of the proton mass. Technical naturalness is beautifully manifested in the smallness of the Yukawa couplings. Does anyone have any questions? Yeah.
So if the uptype and downtype Yukawas for a particular generation were equal, would that enhance symmetry? So you might expect them to be equal?
Sorry, so there's the existence of a selection rule from the breaking of a symmetry doesn't tell you that when the symmetry is broken, the parameters will be equal. The existence of any accidental symmetries when the parameters are equal doesn't enforce their equality. I'm not entirely certain what you're asking, but well, these are the manifest symmetries. We can treat the parameters that break them as spurions, and that's the only thing that controls their appearance. There are various, of course, technical challenges. If you want to use a spurion analysis to organize radiative corrections, there are various challenges associated with the fact that some of the Yukawa couplings are large, but that's about it.
I think you're asking if there's any enhanced symmetries when the up and down quark Yukawa matrices are equal to each other.
Oh, are proportional, or equal, in fact.
And so I think if you turn on
yeah.
there's a custodial SU2 symmetry.
Yeah, so there can be, in particular, you're asking, once I turn on the spurions that break the symmetries, then of course I break these symmetries, but I can turn on spurions in such a way that preserves a subgroup of the symmetries. Yeah, that's completely possible. So that will further control the radiative corrections.
Aren't you changing the naturalness question in the mass parameters into a naturalness question of the hierarchy between the Yukawa?
No, so I want to emphasize, right? Well, Dirac naturalness, we'll see when we turn to the hierarchy problem, which we're about to do now. There are two different levels, right? If in a fundamental theory, right? If in a fundamental theory, I imagine that two parameters are very different in the fundamental theory. Then, as I flow to the infrared of the theory, two things could happen, right? One is that radiative corrections pull the two scales or the two parameters together to be the same, right? So they ruin or erase or wash out any evidence of hierarchies that I had input in the fundamental theory. That's one possibility. The other is that they don't. Okay. So the notion of technical naturalness is if in the fundamental theory there were widely different parameters, that quantum corrections would at least preserve the hierarchy between the parameters, right? Okay. But if you didn't have a notion of technical naturalness, if you had set the parameters to be very different, then generically, as you flowed to the infrared of the theory, they would actually become the same. Okay, so if a theory, so technical naturalness should be less existentially satisfying to you, right? But nonetheless, if a parameter is technically natural, and you can then come up for a reason why the parameter is small, then that should be satisfying, okay? But it's also to point out that there are two different notions of naturalness, right? Very often when people hear about the hierarchy problem, they say, well, why don't you worry about the lightness of the electron compared to the top quark? And the point is that the criteria of naturalness, right, the electron being light with respect to the top quark, that's a just so story, right? That's why does the leopard have its spots, okay? So maybe in the UV there's a reason why those numbers are different, but if something sets them to be different, that's preserved as you go to the infrared. Whereas theories where there's no notion of technical naturalness, where the parameters don't lead to enhanced symmetries when they're set to 0, then there's no ability to understand why numerical hierarchies would be preserved. Okay.
But could you preserve, I mean, is there any way to preserve, in this case, if you have the symmetry, then you preserve the hierarchy, right? If you, I mean, if you have a symmetry and then maintaining that hierarchy preserves the symmetry, then you can say that you will preserve the hierarchy, right? That's what you're saying?
Well, so I'm saying, so first, if there's a symmetry that's not broken, then of course that just sets some things to 0. If it's broken by some amount, then it tells you that even after quantum corrections are computed, that there will be selection rules, right? So a hierarchy could be numerically preserved. And if there's no symmetry at any level when a parameter is taken to 0 or not taken to 0, then there's no ability to understand. So there's no ability to understand why the parameters are different in the UV, but also as you go to the infrared of the theory, there's no ability to understand why radiative corrections don't somehow drag things together. Okay.
Hey, would you agree that the technical naturalness is just it's a halfway point? It's just, if something is technically natural, it makes it more plausible that it's easy to come up with an underlying theory that's fully direct natural.
Absolutely, and we'll
That's fully direct natural.
yeah, the ultimate goal of everything. So the flavor example, right? So in the flavor example, it suffices at this point, once you understand the symmetries of the standard model, to know that Yukawa couplings are technically natural. But if you'd like to make the flavor hierarchies fully natural, that is to imagine in the UV theory there are no numerical hierarchies, then you write down models of flavor. So there are, for example, Froget-Nielsen models where you imagine there are actual fields, so these spurions, right? We say the Yukawa couplings break a symmetry, we treat them as spurions, that gives us selection rules. We could actually literally imagine promoting them into fields, and then having a dynamical mechanism by which they acquire vacuum expectation values, and maybe having symmetries that impose how those vacuum expectation values appear. So that sort of flavor model building takes a technically natural hierarchy and promotes it to a fully natural hierarchy. But as a halfway house, right, if you see a numerical hierarchy in nature, the first question you want to ask is it technically natural? Namely, could I imagine there being an explanation for it that happens at some high scale? Right? If it's not technically natural, then it's hard to imagine an explanation that exists at some high scale, because whatever physics happens between that high scale and the infrared will cause the parameters to be connected and correlated in ways that are unrelated to their input hierarchies. Okay? All right. So those were two examples of naturalness in nature. So let's now turn to the hierarchy problem. And again, as I said, the hierarchy problem is really an example of one of this trifecta of problems in the standard model, or in the standard model plus its extension with gravity, that have a discrepancy between our naturalness expectations and the actual parameters we see in nature. So again, those problems were the strong CP problem. The strong CP problem is somewhat different from the hierarchy problem and the cosmological constant problem, in that it involves a parameter that's not technically natural, but does only have small radiative corrections in the context of the standard model. So it's a little easier to understand what might be going on. But the cosmological constant problem and the hierarchy problem are both problems of parameters that have no real notion of technical naturalness associated with them. And so when we go in nature and we see these parameters are very different from our direct natural expectations, we don't even have the halfway house that allows us to understand how these hierarchies could arise at some much higher scale. All right. So what is the hierarchy problem? So the hierarchy problem, the electroweak hierarchy problem, so I find it helps to draw cartoons when you're talking about the hierarchy problem because it helps you to get a handle on what's going on. The hierarchy problem is that if we imagine our theory of the universe is a theory of quantum gravity, which is as yet unspecified, plus the standard model, there's a scale associated with quantum gravity, which is the Planck scale. We imagine that the standard model is a good description. In particular, the Higgs is a good elementary degree of freedom up until something that is very close in scale to that scale of quantum gravity. All right? So we imagine that this is all happening at 10 to the 18 GeV. And then, as you go down in energy, nothing really interesting happens for a very long time until you get down 16 orders of magnitude later, until you get down to the standard model. And in the standard model, then, 16 orders of magnitude later, we start to resolve the features of the potential of the Higgs. And we see that it generates a scale that is 16 orders of magnitude lower. And in particular, when we get down here, there's really only one vacuum in which electroweak symmetry is broken. And in that vacuum, the Higgs mass parameter is not technically natural. And so we have a hierarchy problem, right? The issue is there are 16 orders of magnitude between what is the apparent fundamental cutoff of the theory and the actual scale that we resolve in the Higgs potential. There's no symmetry of the standard model that is manifest when the Higgs mass parameter is taken to 0. So the Higgs mass parameter is not technically natural. And so we violate both our notions of Dirac naturalness and technical naturalness, right? So the problem of why is the Higgs mass or why is the weak scale much smaller than the Planck scale, in the context of the standard model plus quantum gravity, it's on a different footing from the question of why the electron is much lighter than the top quark, for example, because there's no manifest symmetry when the Higgs mass parameter is taken to 0. Now, it's not the case that in general, right, we don't always worry if we have mass parameters that are parametrically very separated in a quantum field theory. So there are many different classes of mass parameters that are technically natural. A famous one, of course, is fermion masses, right? So if I have a Dirac fermion with a Dirac mass, right, obviously this mass parameter for the Dirac fermion, it respects vector-like rotations, but it also respects axial rotations if the mass parameter is taken to 0. That is to say, if I have a Dirac fermion mass and I take the mass parameter to 0, I can do axial rotations to this Dirac fermion. And so if I have a small fermion mass, that allows me to understand that the fermion mass parameter is a technically natural parameter. But there is no such symmetry, of course, for the Higgs mass. And so for the Higgs mass uniquely of all the fields in the standard model, we have no ability to understand why its mass should be so much smaller than the Planck scale. So there are lots of ways that people talk about the hierarchy problem. The one I think most of you hear when you first learn about the hierarchy problem, and sometimes it's all that people learn about the hierarchy problem, is you hear something about quadratic divergences. And people say things like, in the standard model, all right, the Higgs mass parameter is not technically natural, and it has a quadratic divergence. And if I imagine calculating loops in the standard model, so imagine if I take, for example, a loop of a top quark, I can go ahead and I can compute this. This, of course, gives some correction, radiative correction to the self-energy of the Higgs. But in particular, there's a piece in here that corrects the mass squared of the Higgs. And naively, if I just calculate this loop up to some cutoff lambda, then I find there's a quadratic divergence, and I can go ahead and I can compute this. There's a contribution that comes from the Higgs itself. There's a contribution that comes from SU2 gauge bosons. There's a contribution that comes from hypercharged gauge bosons. There's a contribution that comes from the top quark, and so on and so forth, right? All of the other couplings in the standard model are much smaller. They give subdominant corrections. But normally, when you first hear about the hierarchy problem, this is what you see, right? You're told there's a quadratic divergence. I compute these loops up to some cutoff. I get this large set of corrections. and that tells me that the cutoff of the standard model has to be very low in order for these corrections to the Higgs mass not to involve a fine tuning to give me the value I observe. So how many of you, is this the version of the hierarchy problem that you've been taught, that there's a quadratic divergence problem? Okay, yeah, right. So that's what most of us learn when we learn about the hierarchy problem. That is not a good way, that's not a good place to stop when you think about the hierarchy problem, because this is very confusing, right? I mean, before you learn about the hierarchy problem, before you learn about that, you learn about renormalization, right? Renormalization tells us that in a quantum field theory, sure, we have divergences, but the divergences can be absorbed into the definition of counterterms. The counterterms then allow us to compute finite quantities and relate them at different scales. And so from that perspective, saying that there's a quadratically divergent contribution to the Higgs mass is sort of incomprehensible, right? Why should I worry? This is just the parameterization of a divergence. We know that our normal renormalization and regularization prescriptions allow us to absorb it into the definition of counterterms, and I should never see it when I compute physical quantities, right? So this is one reason why people get confused about the hierarchy problem. They say quadratic divergence is just an artifact of how you've regularized your theory, right? If I chose a different regularization or normalization scheme, I would never see a quadratic divergence, and I would never worry about the hierarchy problem. That's important to pull this apart a little bit more so that you can really understand what the problem is. Now, from the perspective of Wilsonian effective field theory, it is more or less sufficient to stop at this point. Because in the philosophy of Wilsonian effective field theory, what you're really imagining is that this cutoff has some actual significance, okay? That if you have a quadratically divergent quantity, in the context, for example, of a condensed matter system, this UV cutoff would actually be a physical scale in the problem. For example, it might be a lattice that cut off your effective field theory description. And if you had, from that perspective, something that looked like a quadratic divergence, then it would just literally tell you that the mass parameter for this field in your theory was dominated by physics in the ultraviolet. It was dominated by the physics up at the lattice spacing. All of the quantities would actually be finite. If you did some sort of regularization or normalization procedure, that would just be absorbing these large finite corrections and implementing a fine tuning to give you things like pole masses. But from that perspective, right, this is a real manifestation of the size of corrections in your theory, and so you should take it seriously. All right. But of course, we understand the meaning of this contribution should not depend on how we think about our quantum field theory. And in particular, if you don't want to imagine that the standard model ends up with some space-time lattice, then you would like to be able to understand these corrections from a different perspective. Okay. I should actually say, of course, when you normally learn about the hierarchy problem in the form of quadratic divergences, it's a slightly worse problem than this. Right, so this is the problem if you take the standard model as an effective field theory up to some cutoff, and you compute the radiative corrections due to standard model loops. But of course, in addition to this is just the correct radiative correction piece. Dirac naturalness really tells you that your expectation for the mass squared should be some tree level piece that should be proportional to the cutoff squared plus this radiative piece. So at least from the perspective of Dirac naturalness, the problem is a little bit worse. It's not just that we have these radiative corrections to contend with in the standard model, but also generically, we would understand there should be a bare piece that's not suppressed by loop factor. So there's really two questions you should have about this, okay? The first question is, do I have to think about the standard model as an effective field theory, okay? So question number one is the standard model an EFT? And the second thing you should be worried about is what is the actual physical meaning of this apparent quadratic divergence. Okay. So the first question is pretty easy to answer. So we already said when you do this cartoon, of course, we infer the existence of a very large scale, the Planck scale, where we imagine string theory or some other theory of quantum gravity enters. And from the philosophy of effective field theory, that tells us, although the physics at that scale might not be described by local quantum field theory, at least in the matching between the string theory description and the field theory description, there should be evidence of large scales that enters into our effective field theory and really gives us some corrections to the standard model. Okay, so that's the naive understanding, the naive picture we have. Gravity has to have a quantum description. There's some sort of string theory. The standard model will get caught up in that string theory, and so we should really think of the standard model as an effective field theory. But you might say, well, hey, quantum gravity is mysterious. We don't actually have any complete models in which we get the standard model plus a truly complete description of quantum gravity, where we've stabilized all of the moduli. And you'd imagine maybe actually something different happens with the theory of gravity. Maybe quantum gravity goes and takes care of itself, and it doesn't touch the field theoretic sector that is the standard model. Maybe the standard model persists actually through the Planck scale, and then it's a field theory that's good up to arbitrarily high energies. Now, that requires you to ask for a little bit of magic, right? It's in fact a lot of magic. Nobody knows how that really might work. But if it did work that way, you're still not entitled to get away from thinking about the standard model as an effective field theory. And the reason for that is fairly simple. It's that the standard model itself contains the ingredients of its own demise, right? So the standard model gauge group, of course, is SU3 cross SU2 cross U1. We've already seen that the SU3 part grows large as we go to the infrared or small as we go to long distances. And so if we took that part of the standard model up to high energies, that would be fine. The gauge coupling would grow smaller and smaller and be well behaved. The same thing is true of the SU2 piece. All right, but there's a problem when you look at the hypercharge piece of the standard model. So famously, abelian gauge theories, the sign of the beta function is fixed. It's fixed such that the gauge coupling only grows as you go to the ultraviolet of the theory. In non-abelian theories, obviously, there's an interplay between the gauge self-interactions and the matter contribution, so the beta function can have either sign. But in the abelian case, there's only one thing you can do, which is have the coupling grow as you go to the ultraviolet. So you can go ahead and you can repeat the beta function calculation we did for QCD. So you can compute, say, the one-loop beta function for hypercharge. So the answer here has the opposite sign, of course. It has a different coefficient. And you can go ahead and you can solve this beta function. And what you find is, if you just run hypercharge up to arbitrarily high energies, then as you go to the ultraviolet of the theory, hypercharge blows up, hits a Landau pole, at about 10 to the 41, 10 to the 42 GeV. Okay. So if quantum gravity was off doing its own thing and you wanted to think of the standard model as a complete field theory on its own rather than an effective field theory, you would actually be confronted with a blow up of the hypercharge gauge coupling at vastly higher scales than the Planck scale. You could still ask, is that still such a big deal? We don't freak out about the fact that QCD has a Landau pole, the coupling blows up in the infrared. Why should I be bothered by the hypercharge gauge coupling blowing up in the ultraviolet? And there are various ways to think about it, but one thing you can do is you can just say, well, what happens to the standard model when hypercharge hits a Landau pole? And people have actually asked analogous questions, or at least the sort of relevant type of question on the lattice. If you have a U1, the particular case they looked at was actually electromagnetism, but if you just have electromagnetism talking to fermions in the standard model, and you hit a Landau pole in the ultraviolet, you still make vacuum condensates of the fermions, just as you do in the case of QCD. And those vacuum condensates actually break electroweak symmetry. And the value of the vacuum condensate is really about the scale of the Landau pole. So this can't actually happen in the standard model because there's a self-consistency that would break, right? If the standard model were taken to arbitrarily high energies, hypercharge hit a Landau pole, it would actually cause confinement of standard model fermions and it would break electroweak symmetry, not down at the weak scale, but at 10 to the 41, 10 to the 42 GeV. The fact that that hasn't happened, right, that electroweak symmetry is a good symmetry of the infrared, tells us that something has to come in to cut off this picture before we hit this Landau pole. Now, normally, of course, we imagine that that's something like quantum gravity, or maybe it's the unification of standard model gauge couplings, right? But any one of those things requires a modification of the standard model, so we should think of the standard model as an effective field theory. So from this parable, what I just want to emphasize is, even if you want to imagine that quantum gravity is some magic that doesn't provide a cutoff to the standard model effective field theory, the standard model contains the ingredients of its own demise, right? You can't get away from it. And that forces you to take the notion of the standard model as an effective field theory even more seriously, even setting aside the notion of what quantum gravity might do. All right. So what about the second question? So what is the actual physics that we associate with the quadratic divergence? So again, we actually know in a quantum field theory, anytime we encounter divergent quantities, we can go ahead and we can define a regularization procedure to parameterize an infinity and a normalization procedure to define how that relates to observed quantities. So from the perspective of Wilsonian effective field theory, as I said, from that perspective, in that way of computing things or thinking about things, where you imagine that the fundamental theory is finite, you really just have to live with this, right? Anytime you carry out this regularization or normalization procedure, you're just implementing a tuning of parameters to give you the infrared values. But of course, you can also compute similar things in different schemes, and you can see what the manifestation is of this physics in different normalization and regularization schemes. So to do that, I just want to give you a simple toy example, all right? That toy example will manifest why this quadratic divergence is important and signifies sensitivity to physics in the ultraviolet, no matter how you turn out to compute your quantum quantities. All right, so the example I want to work out is a fairly simple one. To see what the quadratic divergence is signifying, we can just work out a simple toy model that just has a scalar degree of freedom in it and a fermion. And because I don't want to get caught up in worrying about what a quadratic divergence means, let's do all of our calculating and all of our thinking in a, oh, is there a question? Yeah.
So I was wondering if I imagine a pure field theory and never worry about quantum gravity, in which I really don't have any lambda pulse at all.
Yes.
And yet, so this field theory is purely well defined all the way up to infinity, and I still have one scalar. Would you still worry about that hierarchy problem in that?
You would worry about it on a somewhat different level, right? So what you would like to do for your quantum field theory to be perfectly well defined is to take the cutoff to infinity. And your expectation of the size of the scalar mass parameter tells you, as you take the cutoff to infinity, the scalar is not a degree of freedom, right? So your notion of what the value of the scalar mass should be, in that case, if there's no other symmetries acting on the problem, it tells you that the scalar shouldn't be part of your low energy description. Now, it's possible when you define your quantum field theory that there could be additional symmetries. There could be, for example, conformal symmetry. And then there would be a reason to understand that the scalar mass parameter should not be proportional to the cutoff. The cutoff can be taken to infinity. The field theory is perfectly well defined. But, OK, so there's several levels to the problem. So you could have a larger symmetry like conformal symmetry that would allow you to understand why the scalar should exist, and the field theory is consistent with the cutoff taken to infinity. But if you didn't have conformal symmetry, you're at least into something of an intermediate realm of the problem, right? You wouldn't be able to understand why the scalar mass was not just directly proportional to the cutoff, but you could at least understand that there are no physical mass thresholds that would be correcting the mass parameter of the Higgs. There is a deeper question that should concern you, which is, in that theory, if there's no manifest symmetry that sets the Higgs mass to be 0 or the scalar mass to be 0, you can't predict that scalar mass, right? OK, so there's nothing that controls the form of counter terms. So it's sort of an intermediate level of being disturbed, right? All right. And in fact, we see that more clearly just in the simple toy example. So for the toy model, to see what the quadratic divergence is actually telling us, independent of our choice of regularization, it suffices just to consider, again, this theory of, let's even just consider a single real scalar that has some mass parameter. We can give it some self-interactions, although that's not particularly important for this example. And then we couple it to some Dirac fermion. And the Dirac fermion, we imagine, has a mass. And then finally, of course, we couple the scalar and the fermion together. All right, so this is just a simple Yukawa theory, right? It's one of the first quantum theories you learn how to handle. And we just want to consider this theory from the perspective of effective field theory and the significance of divergences, at least these nominal quadratic divergences. So what I want to do is imagine we want to ask the question, in order to map on something that looks like the hierarchy problem in the standard model, is we want to imagine taking the mass parameter of the scalar to be very, very small. So if this is energy, we take the mass of the scalar to be very, very small. And we imagine we want to make the mass of the fermion very, very large. And so to map onto something that looks a little bit like the hierarchy problem in the standard model, what we really want to do is work out in an effective field theory framework. We have the full theory, right? This is it. And we imagine, for whatever reason, in the far ultraviolet of the theory, these mass parameters are explained in some natural way. Okay, so these are given to us in the far ultraviolet by definition of the theory. And now we just want to ask the question, as we go from the full theory, which is a good description at energies up here, as we go down through the mass threshold of the fermion, we can match on to a low energy effective theory that is just an effective theory of the scalar degrees of freedom. And because I don't want to get confused about quadratic divergences, it's convenient to think about this in the framework of dimensional regularization with minimal subtraction. So that's a nice scheme because it's a mass-independent scheme. That means that we don't ever have to worry about effects of the ultraviolet coming down to the infrared or keeping track of how that might happen. And what happens when you use dimensional regularization with minimal subtraction? There are, of course, no quadratic divergences. What we do is we imagine deforming the space-time dimension to 4 minus epsilon, and that deformation of the space-time dimension regulates the nominal divergences in our field theory. Then the minimal subtraction part is just the statement that when we set the counter terms, we set them purely to cancel off the poles associated with 1 over epsilon, plus some annoying finite pieces, and everything else is left behind. Now, if we're working in dimensional regularization with minimal subtraction, because it's a mass-independent scheme, if we want to compare physics in the far ultraviolet with physics in the infrared, where we have these different descriptions, what we have to do is we can compute our quantities in the scheme in the far ultraviolet. And if we want to compare them to the same quantities in the far infrared, we have to carry out a matching prescription around the scale m. That's the only way, if you're working in a mass-independent regularization scheme, that's the only way to correctly account for the fact that there are physical mass thresholds in the problem, right? OK, so what do I want to do? So here I have the EFT that just consists of the scalar phi. Up here I have my full theory that consists of the scalar and the fermion. I imagine that the theory is well defined in the far ultraviolet, and I just want to understand what are the size of the parameters in the infrared given the size of the parameters in the ultraviolet. OK, so to do this matching, to compute the parameters that appear in the effective field theory, I have to match across the mass threshold m. What that amounts to doing, of course, is matching correlation functions between the full theory and the low energy theory. In this mass-independent scheme, all I'm doing is matching the one light particle irreducible diagrams between the two theories. OK, so for example, if I want to work out what are the parameters in the EFT for the quadratic terms, all right, so in particular for the wave function normalization of the scalar and the mass parameter of the scalar, what I have to do is in the EFT, I have to match the 2-point function of the scalar to the contributions that come in the UV theory at the scale m. So there's the tree level piece, plus there's a piece that involves a loop of the fermions, so on and so forth. OK? All right. So this diagram, of course, this will be the scalar self-energy in the EFT. It will have a kinetic energy piece plus a mass piece. This will be the same parameters in the UV. This is just the tree level piece in the normalized Lagrangian, plus we have to compute these various loop corrections. All right, so all of the magic is going to happen in this one loop diagram. So we can go ahead and compute it. All right, so if we go ahead and calculate this one loop diagram, we drop our microphone. That would be great, right? Compute a one loop diagram, drop the mic. No. Michael Peskin taught me, by the way, one should never be afraid to compute 2 loop quantities in polite company. So you don't get to do a mic drop until you compute at 3 loops. Okay? Just a lesson for you. I was just getting too excited. OK. All right, so we can go ahead. What do we want to do again? We want to fix the natural parameters in the EFT in terms of all the things that we know in our full theory. And what we have to do that is compute, say, this one loop diagram. All right, that will then set, plus subleading terms in our perturbative expansion, that will set the natural size of the parameters in the EFT. All right. So we can go ahead and compute that diagram. It's just giving us a contribution to the scalar self-energy. We do it in dimensional regularization. So in dimensional regularization, unsurprisingly, by the way, Nima taught me that I should be able to do this calculation without actually calculating anything. I'm not sure I can get the factor of 4 right if I just do it by inspection, but maybe you can do it by inspection. OK. So there's a factor of 4. There's obviously just the factors. It's a loop. It involves 2 powers of this Yukawa interaction. Now what's going on? So there's a 1 over epsilon pole. I'm going to define my epsilon so that I soak up all the factors of log 4 pi and gamma. There's a finite piece. There's a log. The log depends on a renormalization scale. The renormalization scale appears because if we use dimensional regularization, we've deformed the space-time dimension. We want to keep all of our dimensional counting correct, and so we have to introduce a renormalization scale. So this quantity, right, which is a pole, a logarithm, and a finite piece, this multiplies the mass squared of the fermion, and there's a piece that goes like the external mass of the scalar. And then there are pieces that are independent of the mass parameters and have no divergences that are just finite, and other things that are subleading in our perturbative expansion. Okay, so that's it. So we see there's a pole, right? There's a finite piece, there's a logarithm. This will correspond to wave function renormalization, right? Things that depend on the external momenta. This will correspond to mass renormalization. And so now we can just ask, given that this is the contribution of this one loop diagram in the full theory, that will set the values of the parameters in the low energy theory if we do some matching, and we'll do the matching, of course, at the scale m. All right. So we can go ahead and do the matching at the scale m. Let's see. It helps not to be short if you're a physicist. All right, so we want to do the matching at the scale m. So what do we see? OK, so well, before we do the matching, of course, we have divergences. This was just our regularization of the infinities. We have to renormalize the theory. In our mass-independent scheme, our renormalization prescription is just that the counter terms cancel off these 1 over epsilon poles. All right, so all we're left with then are these finite pieces, and the finite pieces are then what's going to determine the matching at the scale m. All right, so in particular, doing matching at the scale m, that drops out the logarithmic piece, and all we're left over is the finite piece. So we go ahead and we do the matching, and it tells us in our EFT we get an effective Lagrangian. Let me write it below the original Lagrangian just for clarity. OK? There's a wave function normalization piece, which we just get purely from looking at the p-squared terms. So that has the form of the original piece, which came from the tree level in the full theory. And then the finite piece that's left over is 4/3 y squared over 16 pi squared. OK, so that multiplies 1/2 d phi squared. Right, that's the wave function normalization matched in the EFT. And then there's the mass term. So the mass term has the form m squared. Again, that just came from the tree level piece in the full theory, plus 4y squared over 16 pi squared times the mass of the fermion squared. And then there are various other terms. There are higher derivative terms in phi. There are quartic interactions in phi. That would correspond to matching higher leg diagrams in the theory. OK, so what do we see, right? All right, there's some wave function normalization that's dimensionless. We're not going to worry about that. But we see the natural size of the mass parameter in the effective field theory, right, computed by matching over the scale, the threshold of the fermion, has 2 pieces. One is whatever we should think of as the ultraviolet value of the scalar mass parameter, and one is a threshold correction that's coming from the fermion mass squared. All right. So that immediately tells us if we actually want to keep the scalar as a light degree of freedom in this effective field theory, if we want to make the EFT mass of the scalar much lighter than the mass of the fermion, then we actually have to tune these 2 contributions against each other to get a total result that is much smaller. All right, and there's no magic here, right? There's no quadratic divergences. There's no confusion about how we regularize the theory. This is people who hate the hierarchy problem. This is their favorite way of calculating something, right? Dimensional regularization with minimal subtraction, get rid of all the quadratic divergences. And what you see is, right, it's not a quadratic divergence. It's the existence of a physical mass threshold that's causing the problem. All right. Yeah. I think, let's see, we can trace it back. So, oh, I might have dropped a minus sign in my definition of the self-energy. I did, yeah, I dropped a minus sign in the definition of self-energy. Very good. Where are you guys in all of this? Who else didn't pick up that minus sign? OK. All right, so here, now here we had an advantage. We had the advantage of knowing the UV theory. So anytime you know the UV theory, you see if you have mass thresholds and you want to describe the effective field theory at low scales in a way that has nothing mixed up with the cutoff, you see you can just calculate these effects, and these effects all are proportional to the physical mass thresholds. OK. By the way, we could have done this whole calculation not using dimensional regularization with minimal subtraction. We could have just done it using a hard cutoff. And what we would have found is, using a hard cutoff, again, if we just did this self-energy calculation with the hard cutoff lambda, we would find, of course, that there was a correction to the mass. It was slightly different in the numerics, but that was a quadratic divergence. So what's going on is, whenever we compute something, we get a quadratic divergence in the effective field theory language. What we really take that to mean is a stand-in for physical mass thresholds, where if we knew the full theory and could calculate in a scheme that had no quadratic divergences, no form of confusion, we would see these effects were actually simply the effects of large mass thresholds. And that would tell us so what we learn is, right, the quadratic divergence, it's just signaling the existence of a potential problem. That potential problem is manifest in any theory where we can actually go ahead and calculate what the effect is. And there's an approximate matching between the quadratic divergence and the coefficient of the quadratic divergence and what the actual finite correction will be. Now, the matching between these two pictures is an art. It's not a science, right? So if you get a quadratic divergence, if you actually have a full theory and you figure out what that quadratic divergence matches onto, the numerical coefficients can be different. If there are multiple scales, there can be other interesting cancellations. But to first order, there's agreement between the expectation for the UV sensitivity that you get from a quadratic divergence calculated up to a cutoff, and the actual contributions you get finite, calculable, nothing magical at all when you actually have the full theory. OK. So that's what the hierarchy problem is, right? There's UV sensitivity. It's signaled by the quadratic divergence. The quadratic divergence is not the problem. But because we are ignorant of the details of the physics in the ultraviolet, it's a stand-in for something more specific that we can calculate if we're powerful enough. And in the examples that we see of old solutions to the hierarchy problem, we will be powerful enough to calculate these contributions and see how they manifest this expectation. There are a couple of questions.
Just a quick comment from you maybe about this. So the couplings here are different in the two calculations. Could that mean that in some cases, a more exotic case, you'd be way off with your naive calculation using just lambda?
You would absolutely like that. So that would qualify as a solution to the hierarchy problem, right? OK.
But I mean, like, is there anything that you can say about that?
So nobody knows. I mean, so this. Well, I would sound like I was parroting Nima if I. OK. Yeah, it's absolutely possible. It would require, so in particular, what you would need to have happen, right? If I have various physics happening at some scale, right? So I have various mass thresholds, and they're not correlated in any interesting way. If I summed up all those contributions, there wouldn't be any non-trivial cancellations, and this mapping would be fairly precise. So to get something surprising beyond that, what would have to happen is there would have to be interesting correlations between all the different terms. So that could be because all of the different pieces actually assemble themselves into some sort of series. And we know, of course, there are many different types of series that have values that are much smaller than the individual terms. So that could absolutely happen. We don't know of any examples where that really happens. But that would definitely be something you would hope to have happen. But other than that, it would, but yeah, there would be some deep underlying mechanism where the UV theory was predicting that the actual value of a normalized parameter was some interesting organized sum of terms that gave you naturally, just from some analytic properties, some much smaller value. But we don't know of examples. Maybe you've come up with one by now, but we don't know of any where that's really the case. But that's the goal. So by the way, in rampant speculation, and maybe I'll say something more about this in the rampant speculation area, this is one of the goals for all of you, right, is to come up, even with toy models, where in the matching over a mass threshold, the actual sum of terms, without some by hand finite tuning or without some organizational principle like asymmetry, where this sum of terms turns out to violate badly the expectations. There are lots of examples, I should say, where just this direct mapping doesn't hold, but they're not ones that give you enormous parametric hierarchies. They give you sort of factor of few hierarchies. Okay.
Hey, can I amplify a little bit?
Yeah.
Totally agree with. People often talk about the hierarchy problem in philosophical terms, but this presentation makes it very clear it's a totally practical issue. But it becomes a practical and meaningful issue when you're trying to find a theory where you can calculate the electron scale or calculate the m squared for some unprotected scale. And perhaps you can.
Yeah, so my next, so I'll get to, let me say more about that in just 1 second. There's one other question. If you left the m squared, if you just had a massless fermion, yeah. So that would be a theory, that's a theory where you just have light degrees of freedom and no UV scale. If there's no UV scale, right, this is something people, the scalar mass, if the scalar mass were 0, well, you would find these diagrams still exist, right? There's still a correction of the scale. So it would be radiatively generated, right?
What you want is an underlying theory which does not allow you to have
Yeah.
an m squared prime. And yet somehow in the infrared you generate one. You
Yeah.
compute one calculus. It's a practical question. And you have to be smart to come up with a theory that allows you to do that.
So in particular, yeah, this theory, because of this interaction term, so if you can ask, I mean, your question can be phrased again in terms of nature of technical naturalness, right? So if we actually look at this theory, we just said, you know, fermion masses are nice because there's an axial rotation. The way I've written it down with the real scalar, it's not actually a continuous axial symmetry, it's a discrete axial symmetry. But this theory has a discrete axial symmetry under which psi goes to gamma 5 times psi, and phi goes to minus phi. Okay, so the fermion mass parameter is technically natural in this theory, but because of this Yukawa interaction, right, the scalar mass is not, and also because of the self-interactions of the scalar mass is not technically natural. So we could have set the scalar mass to 0 in the ultraviolet, right? We would still, these diagrams would still exist. We would calculate them. We would find corrections to the scalar mass. And this is a precise manifestation now of the difference between naturalness and technical naturalness, right? If in my UV theory, I had set these parameters to be very different, this parameter would not be renormalized very different from its initial value, but the scalar mass would be.
Technical naturalness is telling you there's something quite special about the structure of Yukawa.
Well, it tells you that given interactions, free theories have lots of symmetries, right? So if the standard model were a free theory, we wouldn't have we would have this lesser level of the problem, which is understanding the existence of a light scalar, but there would be no interactions that would compel us to see the problem apart from the boundary value of the mass, right? Okay. But yeah, there's two things you should take away from this. I often call this lesson, there's two interpretations of it, which depending on your constitution, you may prefer one over the other. You're perfectly free to take either one. The two interpretations are what I call the strong version of the hierarchy problem and the weak version of the hierarchy problem. The strong version of the hierarchy problem is, again, the fundamental theory should be finite and calculable. I should be able to actually predict the Higgs mass from some underlying degrees of freedom. And in that version of the theory, right, in that version of this picture, there are always masses of this form. There are always corrections of this form. They always enter with the size that's given by our natural expectation. They always tell you there's a very sharp hierarchy problem associated with the scale at which the Higgs mass is rendered calculable. So we'll see that borne out, the strong form of the hierarchy problem, every time we solve the hierarchy problem in a technically natural way, right? So in particular, if we supersymmetrize the theory, then we render the Higgs mass calculable, and then we see that this quadratic divergence is replaced by the masses of new partner particles predicted by symmetries. If we use a global symmetry to solve the hierarchy problem, we find the exact same issue, right? So the strong form of the hierarchy problem is anytime you actually want to predict the Higgs mass, right, you're forced to deal with terms of this form. There's also the weak form of the hierarchy problem. The weak form of the hierarchy problem is for people who don't want to believe that they should be able to calculate everything in the fundamental theory. You say, look, quantum gravity is mysterious. Maybe it does something I don't understand. I'm not going to worry about that. I'm not going to worry about making the Higgs mass finite and calculable in a quantum field theory. The weak form of the hierarchy problem then just tells you, fine, but anytime you have any new physics between the value of the weak scale and however far you want to go in the ultraviolet, any other physical mass scale that couples to the Higgs will give you a finite contribution that you have to live with. So there are lots of examples of those. For example, gauge coupling unification, which suggestively looks like it happens around 10 to the 16 GeV. If that's the case, then there are diagrams of this form that involve extra gauge bosons and extra scalars that give you a correction to the Higgs mass that's proportional to the gut scale. If you have neutrino masses generated by heavy right-handed neutrinos, then there are diagrams of this form in which the heavy right-handed neutrinos can run. Those also give you these large mass corrections. And finally, even if you just have a theory, of gravity and you couple from the Higgs to some heavy particles just through normal perturbative loops of gravitons, you get analogons of this diagram. The details of that is a little subtle. It turns out that those contributions, those threshold corrections, only show up at 3 loops. But basically, you can have diagrams in the standard model where the Higgs is going around. It talks to a top quark. The top quark talks through perturbative gravitons to some new heavy particle, right? And this gives you a finite correction to the Higgs mass that goes like 3 loop factors times the mass of the heavy particle. Okay, so even if there's just some heavy stuff floating around in your theory that doesn't even couple via Yukawa interactions to the Higgs, it just couples through normal gravitons, there's still a finite threshold correction that's of this size. Okay, so that's the weak form of the hierarchy problem.
Excuse me, if you use gravity just as an effective theory without any explicit new particle, you still get write some correction like that?
Without any new particles, yes, but they're always, this diagram, so certainly these diagrams always exist, but if I just had gravity as an effective quantum field theory plus fields of the standard model, these would all be innocuously small corrections, right? Okay. Actually, in detail, it actually goes like this to the 4th over m Planck squared. Sorry, I'm eliding some details. So for the standard model corrections that come through these loops, you can ignore it. But if you had some very heavy particle, let's say some Planck scale fermion sitting out there, even if it didn't couple directly to the Higgs, just the fact that there are gravitons mediating between them give you loop corrections that would be large. So the weak form of the hierarchy problem, it says, you know, I'm not going to worry about finiteness or calculability of the Higgs mass, but if you want anything else beyond the standard model, you still have to contend with those corrections to the Higgs mass. And they're nothing magical. There's no quadratic divergences. They're all finite and calculable. OK. All right, so hopefully now all of you, whether or not you think about the hierarchy problem professionally or not, have a concrete sense of what's at stake here. It's not quadratic divergences. Quadratic divergences are a shorthand way of understanding that the Higgs mass has UV sensitivity. All right? But what we really imagine it's signaling is that there are finite and non-mysterious contributions, either from new particles that make the Higgs mass finite, or from additional degrees of freedom that extend the standard model quantum field theory at higher scales. OK, so whenever anyone tells you that there's no hierarchy problem with dimensional regularization, all you have to tell them, right, is that what you really need, what it's signaling, is sensitivity to the actual existence of UV scales. OK. Yeah? Yeah. So no, you can't. So right. So let's say what you want to do is you want to fix the Landau pole in hypercharge. Okay. But so how would you change the running of hypercharge, right? So you would have to change it in an order one way. You would really want to change the beta. I mean, the leading term in hypercharge, not the 2 loop or higher loop pieces. The leading term, the 1 loop piece, is always going to win. All the contributions you can make to the hypercharged beta function will simply increase the speed with which you hit the Landau pole. So what you have to do is go into a new description where the U1 gauge coupling is not there. The U1 is not there. So you want to unify. So you could be not very ambitious. You could unify U1. You could just embed the U1 into some non-abelian group. You could unify it with SU2, or you could do full unification with SU3. So all of those, right, correspond to some scale at which there are new particles that correspond to unifying into the larger symmetry. And all of those new particles give you these threshold corrections. So it turns out, I think it's probably even a theorem at this point, any modification of hypercharge that you want to implement that would cut off this running of the hypercharge gauge coupling, because of the constraints that we now have from precision electroweak measurements, any such unification still involves finite threshold corrections to the Higgs mass that are somewhat tuned. Okay. So the simplest thing to do would be to put hypercharge in SU2 into SU3, and precision electroweak constraints on that push you to about 10 TeV. And then you can calculate the threshold corrections, and they're quite a bit larger than the value of the weak scale. Okay. But that is, I mean, I'm not going to talk about that a lot unless people are enthusiastic about it, but there is a whole program of the weak form of the hierarchy problem where you just say, let me take care of all standard model couplings, make sure they become small in the ultraviolet, and let me put all of the physics that I need to do that wherever it has to come in. So people are attempting to do that. It's still not very satisfying. To me, the only hierarchy problem is the strong form, right? That the fundamental theory should be calculable. In that case, right, you can't get away with just making everything light. Something has to happen. But there is a whole program of trying to make the standard model take care of itself and imagine then that the UV physics decouples. Oh boy, OK. A couple questions, yeah. All right, well, you haven't asked one yet, so. Yeah, well, so that's because when I have this technical naturalness argument, right? So for example, technical naturalness makes the fermion masses naturally small if the fermion mass is the only source of chiral symmetry breaking, right? But this actual diagram that I wrote down, if this diagram is a scalar, then you can actually work out the details. It doesn't give a mass to the fermions, okay? Or the correction it gives to the fermion masses is proportional to the fermion masses itself. If this is a fermion and it has its own source of chiral symmetry breaking, then that can feed into a new source for fermion masses. It breaks custodial symmetry? Oh, sorry. Yeah, so in the diagrams in the unbroken phase of the standard model, if you write down, they respect the gauge symmetries, right? So there's nothing. If you calculate this diagram coupled to fermions and there were no large sources of electroweak symmetry breaking or chiral symmetry breaking, then of course any correction you get would be proportional to standard model parameters. at the level of drawing this diagram and twiddling the answer, you can't see that, right? But obviously, anytime you write down a self-energy, you know, you could worry about the same thing here. You could worry that somehow this diagram or the diagram for the fermion would give a large correction to the fermion mass, but of course, when you computed the self-energy, you would see that this was proportional to the fermion mass and not to the scalar mass. The same thing is true of that diagram. Okay. But I do want to emphasize, if you're going to use an argument of technical naturalness, you have to make sure that you know all of the sources of symmetry breaking, right? So if a particular subsect of the theory breaks the symmetry by some small amount, if another subsect of the theory breaks it by a much larger amount, and the two talk to each other, then the radius of corrections ultimately will be proportional to the larger breaking. You had a question?
Yeah, I mean, the way you're phrasing it, it looks kind of like you should, like the log calculation is a waste of time, right? So you have a lambda squared, I got a guess at dimensional analysis. You get a 4 pi squared, just a loop factor, and everything else is just numerics which are fully irrelevant to the problem. So people normally use that calculation to try to estimate where new physics needs to exist. But the way it looks like this way.
Well, it's not completely a waste of time, right? So it depends a little.
Way off, right?
Well, so this isn't way off. So it turns out the numerical differences, whether there's a factor of 3 or not, that's not actually way off. That just has to do with, well, you'll notice there's a factor of 3 difference between the 1/epsilon pole and the finite piece. That's not a big deal. But the parametrics that matters is certainly the coupling piece. And the reason why it matters, right? So here's the reason why it matters. Okay, so if you can't control this piece, then of course, I agree it's a waste of time because this piece is the most important. But let's imagine you could either control this piece or argue for this piece being controlled. Then these corrections are coming not through the Higgs itself, but through whatever physics, whatever finite mass corrections are talking to standard model fields that talk to the Higgs. And then that does guarantee those corrections will be proportional to these couplings. So as an example, this diagram, so this gravity diagram, you could actually write down a 2-loop diagram. This is sort of a famous, funny mistake in the literature. You can go and look at V1 and V2 of a paper which estimated these corrections and see the mistake. You could actually write down a 2-loop diagram where you just went directly from the Higgs through gravitons to this heavy particle. All right? And you could ask, what's the size of that? And what you would actually find is this correction is proportional to the Higgs mass squared. And that's because the gravitons are coupling directly to the Higgs. All right, and the Higgs, as the on-shell external particle, if you took its mass to 0, this would, of course, this correction would vanish. Okay? So that tells you this diagram is actually proportional to the Higgs mass squared. This diagram, though, is coupling to an off-shell top quark. All right, it gives you a non-zero contribution, and it gives you a contribution proportional to the fermion masses. But that tells you, right, that then these corrections, so there's one such diagram for every standard model loop. So there are precisely this correction, right, where these relative coefficients appear, where the value of the cutoff is replaced by 1/16 pi squared times this factor, right, times the relative values of the coefficients. So you know, that's the sense in which the quadratic divergence estimate is actually a good one, right? If the new physics is entering not through direct talking to the Higgs, but is entering through talking to any of the other standard model particles, then the relative coefficients do actually give you a good guide to how each one is going to contribute. And again, we'll see that very explicitly when we talk about supersymmetry or global symmetries, where we have a finite contribution, and if you put all of the new physics at the same scale, right, corresponding to uniform cutoff, then they would all enter with these relative coefficients. But it is certainly the case if, for example, some physics makes the Higgs mass finite, and the mass scale of all the different particles related to these standard model fields is different, then of course you should really think of this expression as having a different cutoff for every field. Okay. But using those cutoffs to get some cancellation, that would be a conspiracy that is not natural in the context of effective field theory. Okay, oh, I'm out of time. All right, before we go to lunch, I know we're all excited about lunch. Oh man. All right, I don't think I'm allowed to hold you any longer, right? Or do we have? Okay, let me just briefly, okay. Yeah, right, okay. So we'll just be slightly, the reason why I want to do a little bit more now is because I know the reason most of you are here is the new solutions to the hierarchy problem part, and the more we talk about now, about older ideas, the faster we get to the new stuff. Okay, so I just want to say just a few things. So what this tells you then, so what's the punchline, apart from the fact that the hierarchy problem is not quadratic divergences, it's finite contributions from new mass thresholds. But we don't know, if we don't know specifically what those are, we can at least as a shorthand estimate them from the quadratic divergence. So this now gives you a strategy, right? It tells you if I want the Higgs mass parameter to be at least technically natural, then the standard model has to change at some scale, And if the mass parameter, if we want the size of the parameter not to be too different from what we actually observe, if we don't want too much fine tuning in those contributions, that actually gives us an estimate of the scale where new physics enters. Okay, so if you just look at this diagram relative to what we infer the doublet mass parameter to be, if you want no tuning, new physics should enter at about 500 GeV. All right, 500 GeV to about a TeV. Now, even without specifying what that physics is, right, that tells you should expect something new near the weak scale. That's why naturalness arguments have been the prevalent drivers of searches for new physics at the LHC. But one question you want to ask is it a good strategy, right? So far, it just seems like we're just arguing, we're counting number of angels dancing on the head of a pin, right? There's quadratic divergences. There's just this higher scales, it's bad, something has to come in, right? You want to know, is it a good strategy? Okay, so to know if it's a good strategy, you go into nature and you ask, has this strategy borne fruit before? Okay, so there are lots of examples where it has, but let me just give you two quick examples where the precise form of the strategy has worked out in the correct way. So, so many questions.
Sorry, I was going to not ask this question, but now that you just mentioned that, I can't really ask this question.
Yes.
Looking at that formula, it looks like a Higgs mass, the radiator should be sensitive to the highest threshold, not the lowest one. It will be, but eventually the largest correction might come from the heaviest mass in the spectrum.
Yeah, so if you just have the standard model plus random stuff, then the corrections will be proportional to the highest mass scales. Right. Unless the theory is deformed in a way, right, at one of the intermediate scales, as to change the story, as to erase the sensitivity to higher scales.
Right. So either it should disappear above the threshold.
Yep.
You don't have to worry about that
yep.
anymore. Or there must be consistent some symmetries that actually do
yes.
something.
Yeah, and that's where we get into the normal solutions to the hierarchy problem. But first, I just want to ask about the strategy. Before you even try to specify what happens, you can just ask, how could I imagine, if the guideline is, I want the Higgs mass to be natural, that tells me the Higgs and the standard model has to change at some scale where this estimate of the correction of the Higgs mass is of the size of the mass we see, all right? We use that to expect new physics at some scale. So what you want to ask before you go tell experimentalists at the LHC to spend most of their lives looking for these things is, was that a good idea, right? Was this strategy a good guideline or not? Because otherwise, you have 6,000 people who are very angry at you. Okay. But the answer is yes, and so let me give you two very sharp examples where in nature we've seen this line of argumentation borne out beautifully at the level of mass parameters. Okay. So the first one is just the mass splitting between charged and neutral pions. So this is a beautiful story, right? So we know that pions are actually pseudo-Goldstone bosons of the spontaneously broken symmetries of QCD. And of course, they acquire mass because there's some form of explicit breaking from explicit quark masses. But if we just look at the chiral Lagrangian, of course, the charged and neutral pions should be degenerate. We actually see there's a mass splitting between the charged and neutral pions. Let me see if I can get the numbers right. So the mass splitting between the charged and neutral pions, if I do it at the level of the squared masses, is 35.5 MeV squared. Okay. And there's actually a reason to expect that to be the case. So these are Goldstone bosons of the spontaneously broken chiral symmetries of QCD. But of course, there are interactions in the standard model that violate those symmetries. And so it should be that, a shift symmetry protects these things from any physics that respected the chiral symmetries of QCD. But any interactions in the standard model that violate those symmetries should give you quadratically divergent corrections to the mass of these fields in the EFT. In particular, there's QED. Okay, so QED violates the chiral symmetries of QCD. And that means there's a diagram where the scalars are going and doing their thing. In particular, for the charged pions, there are diagrams where, for example, there's a loop of just the photon. Okay? So this diagram exists just for the charged pions, right, that couple to the photon. It doesn't exist for the neutral pions. The neutral pions don't couple to the photon. And if you just compute these diagrams, then of course there's a quadratic divergence. The quadratic divergence is proportional to the QED coupling. And if you just compute it up to some cutoff in a naive way, that's the answer that you get. Okay. So there's a quadratically divergent contribution to the charged pion masses that doesn't exist for the neutral pion masses. Now we see in nature there's a difference between the masses, or the masses squared. So now we should be able to make a prediction, right? We see an observed amount of splitting. That's what we measure. We know there are quadratically divergent corrections that give us the splitting. So our naturalness expectation tells us new physics should enter the chiral Lagrangian at some scale so that this shift in the charged pion mass squared explains the observed mass difference between the charged and neutral pions. Okay. So if you want this to match this mass splitting, it tells you that this cutoff should be about 850 MeV. All right? If it's 850 MeV, this contribution to the masses squared gives you this mass splitting. And lo and behold, at 770 MeV, you see the rho meson. All right? And the rho meson, if you're studying the chiral Lagrangian, you've got the fields in the chiral Lagrangian, you've got the pions and the kaons. The rho meson is the first time you say, oh, I'm exiting the chiral Lagrangian. I'm starting to enter the whole zoo of particles that are not protected by any global symmetries that are given by the strong interactions of QCD. All right? And so this, in fact, the entry of the rho meson is precisely what cuts off the chiral Lagrangian. And so the natural size of this mass correction is saturated by the appearance of new degrees of freedom. And the size of the correction is precisely what you expect from a naturalness argument. Okay. So the charge neutral pion mass splitting is a beautiful manifestation of the strategy, where the strategy tells us the corrections, the cutoff should be such that the corrections are of the size of the mass that we see. And we see exactly the charge neutral pion splitting is saturated by the quadratic divergence that's cut off when we actually see new physics where we expect it. Okay, the second example, and then we'll go to lunch. The same thing happens, again, it still has to do with the chiral Lagrangian. The reason for that is the chiral Lagrangian is the place where we see scalars and pseudoscalars in nature, right? And of course, we also have a mass splitting between the weak kaon eigenstates k long and k short. So if you just had the chiral Lagrangian, and in there you just knew that the kaons were made of the up, the down, and the strange, right? They were just made of the different partons. Then you could actually go ahead and you could compute diagrams that corrected the masses of the kaons, and you would get things. If you were just computing in the chiral Lagrangian, you would get diagrams that contributed to the mass squared, where if all you had were up quarks, down quarks, and strange quarks, you would find that there were diagrams that contributed to the k long relative to the k short that were quadratically divergent. Okay. So what you would infer from that, all right, so you would get a quadratic divergence. The quadratic divergence in terms of the mass splitting, it's k long minus k short relative to the mass of k long is you can write it in terms of G Fermi, the k on decay constant, 6 pi squared. There's a sine squared theta Cabibbo, and then there's a quadratic divergence. Okay, so that's your estimate for the mass splitting between the k long and k short, coming from these diagrams, which are quadratically divergent in a 3-flavor description. Okay? So you would say, great, something has to happen, again, if I want this quadratic divergence to give me the observed mass splitting between k long and k short. That tells me there's a mass scale, right, that cuts off this theory, that saturates the quadratic divergence, and I want the new physics to enter at a scale that explains exactly the observed size of the k long and k short. So to hit this number on the head, this cutoff scale has to be 2 GeV, and of course we know the charm quark enters at a GeV. And if you compute these diagrams in a 4-flavor with 4 flavors, right, then the quadratic divergence disappears in the mass splitting, and in fact you get a finite result that precisely gives you the observed splitting. So again, this is a beautiful argument where from the EFT, the quadratic divergence rationale told you that there should be new physics at some scale. New physics came in exactly where it had to come in, and it exactly explained the size of the result. And in fact, the pion splitting, this is sort of a post-diction. Now that we understand the chiral Lagrangian, we could figure out how it worked. The splitting between the k long and k short, Mary K. Gaillard and Ben Lee nailed this as a prediction, right? So they actually understood the quadratic divergence, and they understood that there should be a new quark that would cut off the quadratic divergence, and they used it to predict the mass of the charm. Okay, so there's a beautiful example of this naturalness strategy being deployed in nature. Next lecture, we'll talk about first some old strategies, some old naturalness strategies. I only want to spend like half an hour talking about them because that's not why you're here. And then we'll spend a lot more time through the rest of the lectures talking about more new and innovative ways of trying to solve this hierarchy problem. Thanks very much. I will see you at lunch.